afternoon. I'm a rarest of breed today in that I'm an academic. It's a very industry-led day and conference, but it's good to be able to get out here and to be able to bounce ideas and make sure that in academia you're actually supplying research that's actually useful for industries. There's no point doing it if we're not. So I'll be interested to take questions what we're doing here. I'm looking at the impact of climate change on water resources and on water shortage in particular, and how we use uncertainty within climate change projections to be able to make better decisions. So a bit of context, widely regarded that stationarity is now not apparent. Everything that infrastructure that's been built has been based on the idea that the future is the same as the past, and that now is inherently not true from what we know about climate change. We don't know exactly what that future is, but we know that that it is changing. And we know that temperatures are increasing. We don't know exactly how much. We don't know exactly where the precipitation is going, but we know that it is changing. Therefore, that you could say that all of the infrastructure that we have is not necessarily correct as it is now, in that it's not designed for what's coming in the future. The traditional techniques we've used are therefore of using observed instrumental records to make decisions is not necessarily correct, and applying simple change factors, so saying that in X month it will be the amount temperature will be so much greater. We don't take into account the uncertainty in that case. And if we take single projections of the future, we say this is what the future will be like, even though we don't really know what the future will be like, we know within a range. If we take one projection, then we're hedging all of our bets and we can make bad decisions and cause maladaptation. So this is the project I'm doing is based in Staffordshire. It's a small area, and the three aims of the project really are to determine the range of potential impacts of climate change on flows and reservoir levels. So only taking into account climate change here is not integrated. The idea is this kind of work would then be integrated with other pressures, and to assess the probabilities of risk of water shortage. So taking different levels of service and triggering events where a certain service can't be produced anymore because there isn't enough water. And therefore, with that, being able to quantify the most robust policies and adaptations, this is key in that we can select option strategies, infrastructure decisions that are useful regardless of where we go in the future with climate change. So, I don't know if many of you were here for the last session, but there was a brief talk on climate change that came up, and there was three charts we put up of the UK showing baseline period from 1961 to 1990, one for 2020s and I think one for 2050s, and it was on agriculture and saying that this is what the state of agriculture will be like. And that's fine, but the trouble is that means that you're making decisions assuming that is correct, whereas in reality, we have this broad range of what might be the effects. You know, if you have that true value, that point there, what if that isn't right? You know, we don't know how the world's going to develop over the next 50 years. So, the climate is so complicated and we can't model it all. You know, IC dynamics influence weather in Britain, and we don't know how, we can't model that properly yet. So therefore, it is imprecise. So what you're doing, but by making a decision using one specific point, you're being very, very precise, but you're not necessarily being accurate. So what you're better to be doing is to saying, look, we can be approximately correct rather than precisely incorrect. So this is what the project's trying to do. We're trying to develop how we can use these broader ranges of what the climate variability might be to make decisions in water. And we're taking a risk-based approach. So the probability of an unwanted outcome is what I'm going to take as being my metric of the state of water resources in the future. So we're not using deployable output, we're just using certain levels of severity of a water shortage. And we're using drought warning curves to do that, which looks something like this. It's just quickly done up. So you have in blue, you have the actual storage in a reservoir, and then the other lines all relate to a drought warning curve saying below this level, when the reservoir level gets below a certain level, then we will take action on drought. And so what we're using is a trigger. So once the water goes below one of these levels, we will say that is a water shortage of a certain severity within a certain year. And then what we can do is, for all of the different simulations of future, we can try and get an understanding of how that range of water shortage in the future is. So in this case, there would be, that's a hosepipe ban would be triggered, or at least the mechanism for putting into a hosepipe ban would be triggered by the level of the reservoir. So it's quite a simple metric, but it's something as well it's an easy concept, and it's something that can be communicated to the public quite easily. So we say we have this large range. What does that look like? So we need to subsample the weather generator information. The weather generator, I won't go into that, but basically you get day-to-day climate variables, specifically for this precipitation and evaporation. So you get temporal consistency, so you get day-to-day events, but it doesn't, at the moment, the technology doesn't reproduce the most extreme drought events, which can be difficult when you're looking at the highest percentiles of drought. So this is what it looks like, which is fun. If you start on the top left, we've got winter precipitation and summer precipitation. This could be any other variables. You could have temperature, evaporation. Basically, there is this large spread within the simulation. So these are all thousands of different simulations that are all based on the same climate model but have different parameterizations. So they use different assumptions on what's going to happen in the future. And if you look on the top left in the white, that is the baseline period. So that's 1961 to 1990. And then you go through blues in the 2020s, to greens in the 2050s, to reds in the 2080s. And you can tell by the 2080s, you've got this huge spread of, on the right-hand side here, massively more winter precipitation, and at the bottom with, half the amount of summer precipitation. And this is for this specific area in Staffordshire. And you could do this anywhere and you get this same sort of range. So how do we use that to make decisions is the problem. This is showing just subsampling, so this is Latin square sampling, and then we apply that to Latin hypercube sampling. If anybody's interested in that, you can ask questions about that. But this is kind of a simplified representation of that. So basically you take two distributions and you select points, and then you get a small sample of 20 from within these thousands that are then representative of the whole uncertainty range, or most of the uncertainty range. So once you've got those simulations of the future, applying an autoregressive model to create spatial consistency, again, I won't go into this because this is another thing that would take an entire 15 minutes to talk about. But basically, the weather generators are for a point. So you can average it over an area, but you don't necessarily, they don't match up. So if you have two simulations for two areas, the drought events won't be at the same time. So in effect, they're largely useless. So what we're doing is making a kind of primitive model to make them spatially coherent. So you can have two small subcatchments together that produce a drought at the same time. There are much more complicated ways of doing this, but not necessarily ready for industry use yet, because the computationally so expensive, really. And this is just showing it works quite well, really. So the points there are your instrumental levels, and it's just showing that for this subcatchment, we're getting the right sort of variables. That there are problems you can see in the top right with the variation and the variance, and we're working on that. But again, if anybody wants to ask more questions about that, you can. And then using hydrological modelling to get these flow duration curves. So this is flow from a subcatchment going into a reservoir, and it's showing that basically the model that we've created is working quite well. So the blue lines are the weather generator information, and the white lines are the instrumental records. So we've made the weather generator recreate the weather of the baseline period from 1960 to 1990, and it shows that it's good, but at the bottom, because the weather generator doesn't create the most intense drought events, you can see that on the right hand side they deviate slightly, so we don't get that highest percentile of drought events. But overall, I mean, the production is good, the reproduction is good. And then we can apply that to water resource modelling. We're using Aquator in this case. Basically tools that are freely available, well, not freely available, that are used in the industry already. Okay, so it's not producing any more challenges in that respect. This is the area I'm using. There's some catchments in the corner there, in the top right, and a main reservoir. And the reservoir acts as the main drought risk trigger for the area. So that's why we're using it. So if there's a drought at the reservoir, you can be relatively sure that over these two drought zones, then there would be a case of drought. So what we come up with is these quite simple risk matrices, which is a different way of looking at water resource risk. Quite simple, just saying we're having a probability along the bottom here of a water shortage per year, and on the y-axis we have different severities of drought, of water shortage. And what we can just show is that in that baseline period we're producing a certain percentage of the whole range is within these different probabilities. Okay, so on the right hand side, going to 0.2 being more than 1 in 5 years. So for the lower severities at the bottom, that's 85% of the simulation that goes up. So this is for the baseline period, and it's reproducing the what actually happened pretty well, but again, not. You can see there with the instrumental in the red area, it's showing that it's not quite doing the most intense events. And so what we're basically getting is the equivalent of single season droughts, summer droughts, rather than multi-seasonal droughts, because it can't create the statistics to make large multi-seasonal events. It's just not within the weather generator. So we've started doing for the future, and we'll find out what's going on. This is a flow distribution curve and a volume distribution curve, showing that basically by the 2080s, obviously this is the most extreme end, we bring this back to the 2030s, 2020s, that there's huge decreases in water on average. And you can see that the blue lines there, that's the average, the thick blue line is the average over the year. So you've got the probability of exceedance here. It means that if you took the middle, that's the most likely point, but you can't discount the rest of the area. And the volume distribution showing the same thing at the reservoir. You've got these different simulations, but then you can see that the white line, there's a huge decrease there from the baseline. And so for the risk matrices, if you take that to the 2080s at the bottom there, you can see that we start to move into these very severe, severity 1, and more probable, and there's 35% of the range there is within hosepipe bands every 5 years. So that's coming quite severe. And considering that this isn't picking up the most severe droughts, that's showing the kind of severity we're looking at. And you can take that through for the whole century and look how it changes. So to finish off, the outcomes we're using here, basically the idea is to facilitate the use of uncertain climate change information. The idea that you have one projection of the future doesn't work with climate change, doesn't work with environmental assessment, because nobody knows that. Nobody has a crystal ball. We can't understand that. The risk-based approach is needed to increase resilience. And what we can then do is incorporate that into integrated risk assessment. The main thing that would be of use here, that I didn't really put into this, is that you can put your different options and strategies in infrastructure, what you're going to do with your water infrastructure, into the model and see how it then improves the situation. And so you can try and crawl back towards the less probability of drought events by seeing how your options and strategies work within the model, which is why it would be a useful tool for the water industry. So this assumption increases the risk of water shortage in the drought zones, needing to look into stakeholder engagement. It's part of the reason I'm here, to talk to people in the water industry to define what what the option strategies that could be used to improve the situation. And I think it improves upon the abstract concepts of water shortage in terms of communication. Sorry for academia, I haven't put my email up. I haven't got anything to sell, so I don't have any contact information. But it's all in the brochure. So if you have any questions afterwards, then come and speak to me. And thank you very much.